Okay, so thank you very much for inviting me to give this talk at QNLP. I hope it's been great so far. To represent words and sentences, and in particular, I'm going to give like a number of methods that have been done in the community so far for actually concretely building these representations from text corpora. Okay, so here is a summary of the talk. So I'm going to have a short introduction, just talking very briefly about different kinds of natural language processing tasks. Compositional distributional semantics. I'm guessing there have been at least a few talks on this topic so far, so I'll try and skate through that pretty quickly. And then also how to kind of represent, how to use density matrices within that context. And then I'm going to talk in particular about two applications of that. So modelling entailment. Oh, I don't know if you can hear that. My son is in the background, so apologies for that. So modelling entailment and how to build vectors for modelling entailment, and modelling ambiguity and how to build density matrices for modelling ambiguity as well. And so finally, there'll be a summary and further work. Okay, so what kind of natural language processing tasks are there? Well, so we've got text summarization. Natural language inference is where you might have a sentence or a piece of text, and then you want to know whether something else follows from that. Translation is fairly self-explanatory, as is question answering. And in natural language understanding, again, you want to be able to represent some natural language text in a way that maybe a computer can then take action based on the content within that. And you can see that in all of these examples of what we might actually want to use NLP for, being able to represent meaning not just at the word level, but at the phrase, the sentence, and hopefully even like at higher levels than that, document level, is going to be really useful. So the way that we approach representing meaning at phrase and sentence level is as follows. So at sentence level, there's a fair amount of structure, right? So so on the left-hand side here, you've got this sort of grammatical structure that informs you about how words within a sentence combine. On the other hand, on the right-hand side here, you've got a kind of statistical meaning of individual words, and you want to be able to use both of these elements and combine them into kind of one shared representation that really gives you a representation of the full sentence. And how do we do that? Well, what we do is, so one thing that we can do is is the following. We represent the grammatical side using something called pre-group grammar, which has probably been talked about already today. And then the statistical information is represented using potentially vectors. So when we and then the idea behind this is that in both the grammatical element and the semantic element are both instances of what's called compact closed categories. So the way that you can think about this is essentially that the grammatical the way that we describe the grammar and the way that we describe the meaning in vector spaces can both be thought of as having the same structure. And so if we think about just vectors, what that ends up as is that nouns and sentences are represented as vectors, and adjectives and verbs are represented as multilinear maps that take vectors as input and give you back nouns or sentences as output. And essentially what's happening is that the grammatical structure is telling you how to apply these, the categorical structure gives you a functor from the grammar to the semantics that tells you how to interpret the grammatical reductions of the pre-group grammar as morphisms within the meaning category. So these are both instances of compact closed categories. But as well as just syntactic structure, there's also way more structure in language. So on the right-hand side here, we've got, for example, these hierarchies. So, so this hierarchy of language tells you that that a concept like cutlery has instances such as fork and spoon, and this relationship is called hyponymy. So things that are lower down in the tree here are hyponyms of things that are higher up in the tree. On the left-hand side here, there's also ambiguity in language. So if I say the word bank, you don't know exactly what it means. If I say I meet you at the bank to rob it, then that gives you one sense of the word bank. If I say I meet you at the bank to go swimming, that gives you another sense of the word bank. And this is called ambiguity. There's also a slightly more subtle form of ambiguity. So if I say Jumper broke the window and cut herself, she probably broke the glass in the window. If I say Jumper broke the window and now it doesn't close, then she probably broke like the frame or the catch of the window. And this is called polysemy. And it's been argued that actually compositional distributional semantics, so this idea of using vectors, matrices, and other multilinear maps, actually deals with polysemy pretty well. But what it isn't so good at is dealing with ambiguity. So using density matrices to represent words and sentences can actually help with both of these. So not necessarily at the same time. There has been some work by Bob Cooker and Konstantinos, where they have started looking at combining both of these into one shared kind of structure. But I'm just going to be looking at applications of density matrices to these problems separately. So how would we represent a word with a density matrix? So the top bullet there is just a definition of a density matrix. And given a word vector, you can very easily lift it to a density matrix just by taking the outer product of the vector with itself. So cat can be lifted to the projection matrix of the vector associated with cat. And we can then move to mixed states in two different ways. So we can think of different senses of a word or different instances of a word. And when we mix together different senses of a word, that means that we can then start representing ambiguity. But if we have information about different instances of the concept associated with a word, then we can start to represent this notion of hyponymy. Okay, so can you still make this nice mapping between grammar and meaning with density matrices? Well, yes, you can. Since I think time's going fairly fast, so I won't go through this too quickly, but essentially the idea is that now nouns and sentences are represented as density matrices, whereas adjectives, verbs and so on are represented as completely positive maps, and this this construction CPM over FHILB actually also then forms a compact closed category, and so you can do the same kind of mapping from the grammar to the meaning space. So what do these kind of look like? Well, if we write it all out within the diagrammatic calculus in FHILB, then we get these sort of slightly complicated looking diagrams. And the density matrices themselves for nouns and for sentences are kind of doable if you want to build these. So, and we're going to describe shortly how to do that. But then the idea of building the equivalent for verbs and adjectives then gets a bit more difficult. And so instead what we're going to do is just essentially we just build density matrices for each word, and we then combine them using various composition operators. So here we have a number of composition operators. So this phasor and fuzz were talked about by Bob and Konstantinos in meaning updating of density matrices. And in this paper with Gemma de las Cuevas, Andreas Klinger and Tim Netzer, we also introduced a kind of whole range of different operators, corpora, which can be instantiated to kind of different combinations of simpler composition operators. Okay, so how might you model entailment? So we said earlier that you can kind of very simply create a density matrix or a positive operator associated with a given word just by lifting the vector to its projection matrix. And we can then think of more general terms like pet as being represented as sums of more specific terms. And now positive operators have a natural ordering that applies. So we say that A is less than B if B minus A is itself a positive operator. And we interpret this ordering as the hyponomy relation. So in order to actually build these things, we take data from hyponomy relations, which could come from curated resources like WordNet, or you could kind of extract it automatically from Hurst patterns, which are kind of linguistic patterns that give you sort of information about these relations. And you can, so then given a set of kind of off-the-shelf vectors, you can then start building these up together to create the positive operators that you want. But there's also there are also some really nice other ways of doing this. So Manus Sardzadeh, Dimitri Katsaklis, and Esma Balkir also proposed a number of other different ways of building density matrices for entailment. One of those is to look at kind of co-occurrence instead of, so build your matrix by looking at co-occurrence with unordered pairs of basis words. So if you're looking at co-occurrence with pairs of words, you can then map those into a matrix. If they're unordered, you can make the matrix symmetric, and you can then use various algorithms to enforce positive semi-definiteness of that matrix. And then another method that they propose is to take mixtures of the context words of a given word. So if you have dog, the word dog, and if that co-occurs with fur, bark, and run, then you can mix together the vectors for those words to give you the matrix for dog. And these approaches, I think, are particularly nice because they don't rely on this kind of outside knowledge that you need to bring from another system. You can just do it purely on the corpus. So these kinds of representations have been tested against kind of simple, so entailment tasks for simple 2 or 3 word sentences. So you might have these, a sentence like summer finish goes to season end, entails season end. This is true. And what they and also we find is that density matrix models then outperform baselines and other vector-based models. Okay, so how about ambiguity? So ambiguity is a really nice problem. It's said to be AI complete. I think that's a fairly, it's not a technical term, but an AI complete problem just means it's a problem that is requires a lot of knowledge about various things that are going on in the world. And so one problem is to disambiguate just one word given a context. So here we've got, you can disambiguate bed. But another problem is then also to disambiguate every single word in a sentence. And that problem is difficult because if you think that you need to use the context of a particular word to disambiguate it, then to disambiguate every word in the sentence, you need to consider all possible contexts. And this this paper here argues that this is actually becomes computationally very complex. Now, the nice thing about compositional distributional semantics is that we want words to disambiguate in the process of composition. So we don't want to have to go through, do the disambiguation, and then compose them. What we want to do is we want that disambiguation to happen automatically. So 1 minute, apologies. Yes. So, yeah, so using density matrices for lexical ambiguity was originally investigated in this paper by Robin Piedele, Dimitri Katsaklis, Bob Cook, and Manoush Sarjazadeh. And they really carefully kind of laid out the formal background of this, which you can go and read. It's a really, really good paper. And they did a small experiment. So they built density matrices by taking vectors of the context words then clustering those vectors. So you can imagine, so they cluster the vectors. So you can imagine that you've got a number of different context words. You apply some kind of clustering algorithm like k-means clustering, and you see that, and then you see that you get a certain number of senses coming out of that, and you then mix those together. And the experiment that they did was then to look at how the von Neumann entropy of density matrices then evolves in the composition. And what they find is that when you compose the noun with the verbs, the entropy of the composite does indeed decrease. Now, what I also want to present to you is a neural approach to building density matrices for lexical ambiguity. And this is work by Francois Meyer. It was his MSc project at the ILLC, University of Amsterdam. And essentially what we do is we use a modification of a word-to-vec algorithm that learns multiple senses for each target word. And then those senses are combined to form density matrices. So there's a sentence similarity task, and the idea behind the sentence similarity task is that you have an ambiguous verb, and that ambiguous verb can be disambiguated by its use in a sentence. So for example, here where we have family move hotel, that's the wrong sense of the word run. So in this case, run does not mean move. On the other hand, if you have like people purchase house, that should have the same sense as people buy house. There, it's got the same meaning. I'll skip over the kind of word to vec basis. Essentially, it's a way of learning vectors automatically from a given text. But what we do is that instead of just learning one vector per word, we learn multiple vectors for each word, and we kind of encourage them to cover different senses. And we get really nice results on this. So we test against a number of vector-based baselines, also sentence encoders, including BERT. And our best model outperforms all other baselines on 2 of the 4 data sets, and then outperforms on this one here. It's not statistically significantly different. So so the nice, and oh yes, and then we do a really similar experiment as well. Another similar experiment where we look at how the von Neumann entropy of the verb kind of evolves in composition. And we find that with the phaser model of composition, the von Neumann entropy always decreases. Okay, so I think I'm out of time. So I'll just talk about some summary and conclusions. So what we find is that using mixed states can help us model more aspects of language, such as hierarchical structure, entailment, and ambiguity. There are lots of methods for building density matrices, but I think so, and I think that this is a really a nice area for research. So how can these be improved or extended? Maybe the neural method can be adapted for hypotonomy and entailment. Of the different composition operators are, and also what additional structure can be added to this. So I've started looking at negation. We've also started looking at metaphor as an instance of ambiguity. So thank you all very much for listening. Apologies for the interruptions, and thank you to the NWO who funded some of this work. Thank you.
Thank you, Martha. Let me check the Slack. You're getting a lot of claps for multitasking. So good job. Someone is suggesting William Blake's work that uses density matrices.
Oh, yes, yes. So apologies that I didn't cover that. Yes, he does use density matrices. I think it's in a slightly different context to this, but yes, they also do that as well. I think they use it possibly more for the syntax.
Yeah, Bob says that they use it for extending the parameter space.
Right. Okay.
Okay. Yeah. I guess there's a lot of models you can make, right?
Yeah.
Let's see if there is any other questions. Otherwise, maybe I should ask one. Stefano says, I'm interested in your last comment on metaphors and ambiguity.
Mm-hmm. Yeah, so
he says, I'm interested in your last comment on metaphors and ambiguity. Would you be able to comment a little on what you've discovered so far?
Yeah, so the idea is that in some cases, so metaphors that are quite well used in text already, so conventional metaphors like the word bright, for example, to mean intelligent. You could think of these as just, again, another kind of ambiguity, right? So actually, if I go back to this slide, there's under the word insects, you can see that one sense of insects is a small air-breathing arthropod, But another sense of the word insects is a person who has a nasty or unethical character. So, and that's clearly a metaphorical kind of use of that word. So the idea there is that actually, if we just think of metaphor as an instance of ambiguity in these kind of well used cases, we can model metaphor within the same kind of framework. In terms of findings, I don't actually have any findings yet. So we've started, I've pulled together a small data set to look at how people rate similarity using with different metaphorical words. But yeah, that's definitely still work in progress.
So the idea is that you treat metaphorical meanings as synonyms, just as you would use like ambiguity over synonyms, right?
Yeah, well, it's not
Because you say,
yeah, is it synonyms? Yeah.
I think
synonyms. Yeah, you treat it as a kind of ambiguity over synonyms.
Okay, thank you, Martha. Let's see if there's another. Alexis, when do we do experiments on quantum hardware? I heard they were really good at density matrices. Okay, it's like, yes, we're gonna do it. That's the answer, I guess, right?
Yeah. Yes. Yeah. Of course.
Yes.
Yeah.
Of course.
Yeah. Oh, and I should. I can point out actually that in this neural method that we used, we actually used very low dimensional vectors. So the density matrices were 17 by 17 in the end. So that, I guess maybe that's not too not too high.
Oh, okay. Yeah, that's encouraging.
Yeah.
Cool. Yeah, I think we're out of time and out of questions. So
okay.
thank you again.
Okay, thank you all.
Very nice talk.